Hartman was willing to share this knowledge with us. He have decided to divide the two meetings to two. In the first meeting, which is today, we'll learn a lot about the STEP as a methodology. And on Thursday, we will discuss case studies and see how STEP and the other methods, right, the STPA, STPA, and the CAST are implemented. So, Dr. Hartman, thank you very much again for willing to present to us. And I am opening the stage to you.
Okay, thank you, Nir, and thank you for inviting me. And okay, let's talk. And I intend to present you a very short introduction to STAMP, which is a safety model for complex systems, an integrated approach to safety and security. But I will not talk about security based on system theory. Yes, and my name is Daniel Hartman. Okay, I will start with a very brief introduction to safety, and I will present to you mainly my view for this, especially for this lecture, because there are some new concepts, some new ways of thinking, and I would like first to start with this. And of course, first we need to have a common definition for the wording that we are using. Yes, so for us, safety is just absence of any losses. Yes, any losses that matters to some stakeholders within a given system. Yes, and therefore, this the wording losses can be accident, mishap, disaster. So from a very small mishap up to a disaster where 10,000 or 100,000 or even million people can die and so on. So safety is always absence of any losses, and any losses which are undesired and unplanned, yes, and result in a loss. And it includes loss of human life or injury, of course, property damage, environmental pollution, but also negative business impact. For example, damage to reputation, mission loss, product launch delay, or any other delays, legal entanglement, bankruptcy, etc. So all kinds of losses. And again, we include in our losses unintentional, and then we will refer to safety, or intentional losses, which are part of security, cybersecurity, and so on. So in STAMP, in our world, safety and security are just the same. Yes, we treat them, well, not exactly the same, but they are within the concept. But before, I'm a geologist by training, by the way. So I like very much to show you pictures and illustrations. So let's think about the Thanksgiving turkey. Yes, you know that it starts from an egg, and then a chick, and then it grows up to a full-grown turkey, and suddenly you have it on the Thanksgiving platter. So obviously the turkey has no safety in his mind. And safety for us, you have to know and think before you act, before you do something, and before you design things, before you plan things, and so on. Yes? Otherwise, we will end like this Thanksgiving turkey. And I'm Israeli, so I will give you two disasters that influence much the way we think about safety in Israel. One is the Carmel disaster, fire disaster. By the way, if you don't know, Mount Carmel originally is in Israel, not in California. And at this disaster, 44 people died, victims, but actually there were 3 different accidents within the same location. Well, this is a lecture for itself, but it was a very expensive lesson in risk management and system safety. Yes? And then we had a few years ago, 2 years ago, another disaster in Israel, also on the top of a mountain called Mount Meron. It was a religious ceremony where 10,000s of people gathered together, and it happens what happened, and there were 45 victims and more than 150 injured people, yes? So life presents us very severe accidents, disasters, but is stamp only for this? No, stamp can be for any type of losses, as we said before. Here we have an example where a few cars were involved, and one of them is the Tesla car, and partly autonomous or driver assistance system. And one of the reasons that they found was failure to maintain a safe distance, yes, was one of the main reasons. I bring this accident as an example because later on in the lecture I will talk about safe distance and how we use it to clarify some of our concepts. And also a very minor accident or loss event in Israel also. We have also already electric cars, and one day the charging station didn't function, and of course it can cause a big problem and can lead to various accident loss events if a car, an electric car, has no fuel and cannot drive and reach the goals that it should reach at that moment. So I started talking about safety, accidents, and I like very much to refer to a book published about 25 years ago by a group of doctors, medical doctors, and the title of the book, you can find it on the internet, is "To Err is Human." So medical doctors discovered they err. Of course, people die because of these errors, and it's human. But this concept has nothing has no meaning, because the concept should be, and the concept that I am intend to provide to you to talk about is to err is human, okay, but to learn from errors is safety or viable system. A system which wants to be viable, okay, it can err, it can have errors in it, it can have accidents, disaster, but if we are clever, we have to learn from the errors. Yes, so safety is about learning from errors and implementing what we have learned in what you call or we call risk management, and we'll talk about. Okay. And we have a problem, a human problem, and I quote Nassim Taleb. Maybe you heard about him. The book he's writing, one of the famous is the Black Swan, and he is writing, "You will never fully convince someone that he is wrong, only reality can." So actually human beings have to suffer. We have to go through loss events, accidents, and so on, because otherwise we think that we are perfect. We have some biases, yes? And actually our job, well, myself as a scholar, academic, and you, when you are finished as professionals, either in the academy or the industry or in some organization, is to understand that we have to learn from errors, but we have also, in our mind, we have some problems. Yes, one of them is called hindsight bias. Yes, human beings have many biases. Kahneman wrote about it. Other people, psychologists and so on, talk about it. I'm just interested now in something called hindsight bias. So we have a loss event. Yes, something explodes. It's just an illustration. And immediately afterwards, everybody knows what went wrong. Everybody can say, oh, this was wrong, he is to blame, everybody. Yes? But our place is elsewhere. Our place is before the loss event, before the accident. Yes, we have to look at the system, the best viewpoint is, of course, when we have a concept for a system or when we design a system, when we start to build it and so on, and to look for all the possible places where something can go wrong. So again, we need knowledge and system thinking before we act, before we start dealing, and then we will have probably a better system, safer system. So we have accident, but actually the life cycle of accidents. I mean, we have car accidents every few minutes in the world. We have airplane accidents probably every few weeks or every few months in the world. So accidents are coming again and again and again because there are some small changes in the system, something happened and so on, and we investigate them. But we don't want to investigate because investigation has a connotation of something not good. We want to analyze the accidents, yes, and if we will do that, after a while, we will find that we increase the data related to the accident, the information, and the knowledge, and we will see that we have a learning curve where the number of incidents or accidents will slowly go down, yes, until a point where the system is almost perfect, but there will be always some accidents, yes? So we have to analyze and we have to understand our accidents if we want safer systems, yes? So our mission, or my mission as a safety academic or professional or whatever, is to create or to generate a socio-technical system as learning organization. If we learn from our mistakes, from our accidents, disaster, and so on, yes, then we are a better organization or better system. And we can see it in data. So I just looked in the internet, and you can see here a very nice learning curve or safety learning curve in the petrochemical manufacturer, some parameters, and they go down. It means that the system learns from its own mistakes and is getting better and better. Is it enough? It's something that I don't want to say about it, but they are getting better. And you can see it also in all other type of accidents, but it's not enough, of course. But we have a problem because we live in modern times and everything change very quickly. There is disruptive technology and so on. So if we have a learning curve at a certain point of time, and we have something called inflection point, we have a disruptive technology, yes, then we have again a new learning curve and a new learning curve and a new learning curve. So once you are in a given domain and you say, okay, I will do what Daniel Hartmann told us and we will draw a learning curve, but you have to ask yourself, is the system in a kind of a steady state or it has changes in it? Because if it has changes in it, then you'll need probably a new learning curve. So it's more complex than it looks at the moment. Okay. And then there is another problem related to loss event, accident, and so on. If we see two cars crashing, yes, we know that there was an accident. Why? Because this kind of a feedback loop, we see that something is accomplished very fast, and we know that there was an accident. Within few seconds or even parts of a second, we know that there is an accident. But we have also situations where this feedback loop of information is very slow, yes? It can take 10, 20, 30 years for some accidents to show themselves. For example, a sickness called asbestosis. So if people inhale asbestos fibers, yes, they will get sick, very sick, and will die after 20, 25, 30 years. Yes? So if this feedback loop accomplished very slowly, we are talking about exposure, or maybe it needs another 10, 20, or 100 years to be accomplished. Or maybe there is no feedback loop, maybe there is no accident. So, for example, for many years, people were talking about the risk of the radiation of smartphones. I don't know. I read a lot about it. Is there any risk in it or not, and so on. So again, we have to be aware that not all accidents that we perceive as accidents are materialized already, and we have to understand it. Okay, so because very often, and we'll talk, they are latent in the literature. They call them latent accidents. Yes, they are hidden somewhere, and you can find it everywhere in the high-tech industry, in the aviation and space industry. We have an airplane is flying for many days, or hours, or even months, and then suddenly there is a disaster accident, and they trace it back to some problems in the design of something within the airplane. For me, it was a hidden accident. In transportation, in software, I mean, we know that all the time we have problems with the software because there are all kinds of problems in it. And they are exposed, of course, in the software industry. If it's not a critical machinery, we just fix it and we go on. In the justice system, in the United States, you have the Innocent Project, and they have found out with the help of DNA analysis and so on, that about 5% of people who were convicted to life or even were executed were innocent. Yes? So if someone innocent is put in jail, for us, it's an accident. I have actually a friend in Israel, a professor, a law professor who is writing about it. Yes? And in the health system, in nourishment system, we'll talk about water, the next meeting, personal care, environmental system, environmental change. We are talking now for 20, 30 years about climate change and so on. Is it really? Is it not real? How long it will take to develop to a real catastrophe, or maybe never? And also I would like to put here decisions, bad decision making. Someone can make a decision today, and only after 50 years, people will find out that it was a very, very bad decision, and actually something will happen in the future because someone made a wrong or bad decision now. Okay, so this you can read. I will go on. So if I can summarize for the moment now, we need learning culture. I know that you were talking in Nir's lecture about safety culture, SMS, a safety management system. Something very important is a safety culture, and within safety culture, the learning culture, yes? So we have to know to analyze accidents in a professional way. We have to, some lesson learned, and we have to apply best practices, but best practices that are modern, not best practices that people developed 50 or 80 or 90 years ago. We have to know that some of the methods and models, thinking models in safety are old, are not relevant to the modern world. Okay, so the next step is what motivation for analysis of loss events and accident and having safety. So you probably will think that I will talk about ethics and life and so on. No, dollar, money, yes? Of course, life matters. Of course, everything that we should prevent people being killed and injured and so on, it's very important. But we live today in societies, in countries which look at the economics as something very important, and therefore money is very critical. There are a lot of publication and research about the ratio between investing in safety and the cost of accidents, yes? And we have a saying, if safety is too expensive, try an accident. Accidents will be always more expensive than the sum of money that people should have put into the safety system. And here we have to start thinking in life cycle. So if we have the life cycle, concept, requirement, design, build, operation, and so on, and we take two parameters, effectiveness of changing things and the cost of changing things, yes? And we have one curve, cost of design changes, and the other curve is ability to impact cost and performance. So if we find already in the concept or requirement phase of building, creating a new system, we find problems, yes? We can fix them at very low cost, yes? And they are at very low cost. On the other hand, if we operate already something, yes, the cost of changing it will be very high. Yes? So, of course, if we can implement, if we can use tools and models for safety in engineering, or not only engineering, in management, in leading a country and so on, already in the early phases of life cycle, it will be more efficient and less cost, it will cost less. Now, we can divide this life cycle into two parts. One part we call solution-free stage, and the other one is solution-oriented stage. Yes? The solution-free is very cheap, costs very little money. So if we can have influence and make the system already safer at this stage, we have a lot of benefits. Now there's a problem, because for the first part of creating a new system, usually systems engineering are responsible. And safety professionals usually are involved in the operation of a system, yes? And this is not good, because we want safety thinking and safety professional to be able to influence the system engineering and the engineering of new systems. So again, if we take the life cycle and different activities that we can do, these early stages, the stages where we don't have already invested in material, but we have just paperwork and computer design and so on, we can influence the requirement and so on, will save a lot of money and will get safer system. And Nancy Leveson made some research, and in red, her statement, virtually every accident in the past 30 years related to software can be traced back to requirement. And probably the same can be also not only related to software, but also to hardware or to other systems. Yes? So our focus should be here and not here. So we have to think in life cycle, different stages in life cycle, and the good news is that actually one of the methods that we will talk about, stamp method, STPA, can be used from the beginning, from the early concept where we have only functional thinking about the system. We can already start having safety in it, only from functional thinking, without having real something tangible at the end. Okay, so we need new approach to safety, because traditional safety engineering approaches developed for relative simple mechanical or electromechanical systems. I will illustrate it in a few slides. The nature of accidents in complex software-intensive systems is changing. Yes, we have different type of accident now, and the role of humans in modern systems is changing. And I know that you are dealing a lot near with human, how do you call it?
Human aspect of safety.
Yes, and I'm sure you are talking about it. The role of humans is changing. Yes, humans are not pilots in an airplane, are not. I mean, there are some automatic things that flies the airplane, and the pilot is just keeping an eye that everything works, hoping that the software engineer and the other engineers have created a safe system. Okay, so it's obvious that everything changes, and we are again holding a smartphone, and we are not holding this type of telephone used 100 years ago. So we should change also when we are talking about safety. So going back to safety and illustrate things, I'm sure everybody knows the meaning of risk, yes, how it's defined in many, many books. I have at least, I think, about 30 books about safety. In all of them, risk is defined as the probability multiplied by severity, yes? And we can illustrate it, yes? Let's say we put this little man in a picture or in some pictures, and here he stands before this pit. If it goes further, it will fall, and with high probability it will fall. The impact will be low. Here the probability is low, and the impact is also low. Here the probability would be low, but if it do fall in the pit, the impact will be high, and of course here the impact is very high and the probability is very low. So this is a concept. I'm just illustrating it. What the meaning of risk is equal probability multiplied by severity. But is it a good concept? I will try to convince you that we have better concept for it. Okay, so we need new approach. And one of the problems in common safety is thinking in chain of events, yes, the domino effect and so on. Chain of events model is too simple for today's complex systems. Engineering has fundamentally changed in the last 60 years, and it's not going back. Accident prevention or analysis technique based on linear thinking will have limited usefulness. So it's not that we say all the other methods are wrong and don't use them. No, we say they are good, but they have limited usefulness. There are better, more efficient models and methods today. And we know that accidents happen with no component failure, and I can give you examples for it. Accident happen with no software failure. Software is perfect, but still software causes the accident, and we need something new, beginning aware with the understanding that safety and reliability are not the same. At the early stages, 100 years ago, when we had mechanical systems or electromechanical systems, safety and reliability were connected. But today we can have a safe system and it is not reliable at all. Okay, we can have a very reliable system, but it will be not safe at all. And the tools that we use or the methods that we use for reliability, we should not use them for safety, especially the probabilistic approaches that were taken from reliability engineering and used in safety engineering. Okay, so now finally we are at the STAMP model and its tools. What is STAMP? So much talking about it. STAMP is just acronym for System Theoretic Accident Model and Process. Nancy Leveson, about 24 years ago, published the first paper or the first something written, and she is actually demanding change in paradigm. If the old paradigm is that safety is about preventing failures, she says, no, I don't want to prevent failures. I want to enforce safety constraint on system behavior. So again, to the illustration that I showed before, failures are risks. So we don't want to prevent risk. We want to enforce safety constraint. And for this enforcement, we need a new something we call hazard. It's not the hazard that you understand from a daily speed and so on, yes? I will show you a definition, or Nancy Leveson definition for hazard. Yes? But once we have it, we understand that according to STAMP, that safety should be, or accident prevention should be treated as a control problem and not a failure problem. And again, her thinking is as engineer, yes, she wants to control the system and not to prevent failures, yes? And losses are the result of complex dynamic processes, not simply chain of events. So everything is changing, as I said before. And actually, if we analyze again and again accident, disaster, loss events, and so on, we find out that they arise from very bad decision-making, design flaws, or even slow migration of the entire system toward a state of high risk. And I will talk about it in 2 days. Okay, so in STAMP, we have some changes. We enforce safety constraint on system behavior. We focus on the entire complex socio-technical system. And again, I will have to explain this parameter or this phenomenon. We have hierarchical functional safety control structures, and STAMP is about verbal logical safety constraints. We have no mathematics at the moment, no probabilities, but only logical thinking and expressed in words. Safety functions are transferred top-down in this socio-technical system through the entire system, from the highest level hierarchy, which actually legislation, to the lowest level hierarchy, which is the floor, and so on. And STAMP has 2 innovative practical tools. So STAMP is the model of thinking, and STPA and CAST are tools. And we can see it here. STPA is one tool, system theoretic process analysis, built on STAMP model. And again, if you ask yourself, what the hell is STAMP model? It's just saying that accidents are caused by inadequate control. This is the model. Of course, it's more complex, but enough, this short sentence to explain it. And we have the method. STAMP, STPA, hazard analysis, but hazard with a certain definition. And in this hazard analysis, we ask ourselves, how do we find inadequate control in a system? Yes? Again, very, very brief, very short, but this is the essence of the method and of the model. And then we have another method called CAST, causal analysis using system theory. So we have STAMP model, we have FTPA, and then we have another method, as I said, CAST, it's accident or loss event analysis. And here, the accident is materialized, is something real. So we ask ourselves, how do we find inadequate control that caused the accident? Yes? And I have a very nice illustration where we bring all together. Yes, we have the STAMP model, we have the CAST accident analysis, we have the STPA hazard analysis, and the STAMP model is based on system theory, systems engineering, socio-technical system, control theory, and emergent property. Safety, according to Nancy Leveson, in our thinking, is emergent property. I will explain it in a few slides. Okay, so actually this is enough, of course, without any details, but this is the essence. This is the model and its tools. Okay, so now we go back to the illustration that I showed you before, and we put the hazard before the little man, yes? And still, it's not the definition, but just to understand, hazards have the potential to lead to the loss or to the risk identified, yes? So, as I told you before, we want to prevent things in STAMP. So we don't want to prevent this little man fall into the pit. We want to prevent him approaching the pit, yes? Therefore, the wording for the hazard, or part of it, will be so the hazard is not keeping a minimum distance from. So as long as this little man will not keep the distance, he can fall into it. But if he will keep the distance, he will not fall into it. Yes? Okay, and now we put on this hazard, we put a second, a new concept, and it's safety constraint. Safety constraint has the potential to prevent the hazard and the losses risk identified. So instead, we find the hazard and we turn the hazard into safety constraint. And the wording will be, this little guy must keep a minimum distance from the pit, and if we will keep it, he will not fall into it. Yes? That's all. How to do it, it's something else. But again, just for our mental, for the way we think about safety, we are a step before the risk, and we want to be there. Okay, so now if we have the concept of risk, and risk in the old way can, via different probabilities and severities, lead to loss events and so on, now we have the new concept of hazard and of safety constraint, yes? And we will go further with it, and of course I will all the time ask you, do you want to go this way or do you want to go this way? Okay, so now we need some definitions. According to the STAMP model, Nancy Leveson definition, hazard is a system state or set of conditions that, together with a particular set of worst case environmental conditions, will lead to a loss. And addition, hazard must describe the states or conditions which the system can prevent. So if we want to prevent the damage of a hurricane, we cannot. A hurricane is no hazard, yes, because we cannot prevent it. Or if we construct an airplane which flies at 30 kilometers high in the atmosphere and the pressure is very high, we cannot prevent the pressure of the atmosphere, but we can build the airplane in such a way that will be able to stand the pressure, yes? So hazards should be, only if we can prevent them, we will define them as hazards. And based on the hazard, we have new definition for system safety constraint. System safety constraint characterizes the system states or behavior required throughout the system life cycle, starting from the design process in order to prevent hazards or prevent hazards from materializing as loss event. Yes? From the design stage, safety constraints apply to two different states of the system. We have first, safety constraint treats the realization of the hazard proactive action to prevent a loss event. For example, we want to prevent collision between two cars. Yes, so the hazard would be not keeping safe distance. The safety constraint is must keep a safety distance. Now, sometimes we don't keep a safe distance. So the second safety constraint handles the creation of the ability to minimize in advance the damage of that may occur if hazards is realized, proactive action and so on. So for example, I'm going to the idea that the engineers developing a car, yes, they have to know that in advance they should prevent two cars to collide, but if the cars do collide, then they should prevent the second proactive actions to prevent the damage, so safety belt or the airbag and so on. Okay, and again, we need to define the hazard because from the hazard, from the sentence or from the putting it in words, we transform it into safety constraints. So there is a relation, a very tight logical relationship between these two parameters in the system. Yes. So as I said before, I want to provide, or we want to provide not to provide, but to
prevent.
To prevent. Yes, I'm getting tired. To prevent the collision between the cars And if there will be collision, then there will be loss event, harm to people, death or serious injury, and therefore we will define hazards. There are few of them, but we just look at one hazard, not keeping a minimum distance from another car or another object in its path. Yes? So this, both drivers should know it. And then we take the hazard and we transform it into safety constraint. Maintaining, it's actually the same sentence, but transformed. Maintaining a safe separation distance between a car in motion and any other factors in its path must be incorporated in the design and operation, yes? So there is always a must be or shall be, depending on the industry and so on and so forth, yes? And now this we can implement in the system already at the functional stage. And we should put it into legislation, regulation, standardization, work procedures related to the vehicle itself, to the infrastructure, to driver training, to drivers, and so on, and everywhere. If everybody will know about these safety constraints, there will be no car accidents. But not only such a frontal accidents, but also all kind of these accidents. But actually we can generalize it. Yes, we can prevent all this type of not keeping a minimum distance. Yes, and we can go further, of course. We can also understand and prevent, if we apply it in a correct way, that an airplane crashes into the ground, or two ships crashes together, or train crashes. And again, this is a lecture for itself. We have a few years ago in Israel, a train crashed with a chemical on it, bromine on it, and it could be, luckily it was not a big catastrophe. Okay, so this was about the hazard, safety constraint, and so on. Now let's talk about the control thing. And the control thing is as in engineer control theory, yes? We have a control loop, we have a controller, we have a hazardous process. Sometimes we work through an actuator. We send some control actions, we get via sensor feedback, and this is our control loop. Yes? And of course, it should go forever if we want to keep the hazardous process in a safe state. I don't have time, but you also have to think about the time that the control action is going down and the feedback is going up, but will not go. But you can see that the controller has a level above him, and the hazardous process can have a level beneath it. So it's not just one control loop, but it can be many control loops nested in different ways depending on the system that we are analyzing and studying, yes? And within this control loop, as I said before, there is a controller at certain level, let's call it level N1, and the control actions, it's actually what to do, goals, policies, constraints, commands, resources, yes? If I give a command, but there are no resources to implement it, so if my computer would have no electricity, it will not be able to execute all the commands that I give him. And responsibility. The controller has responsibility for its control actions. The hazardous process has to send by design. What happens in the hazardous process? All this listing, and by design, it needs to have the accountability to send the feedback back to the controller. And again, as I said, this is the concept. So we look at the system as built of many such control loops nested and so on. And this is, if we do it in a proper way, we get a safe system, but we'll talk about it, of course.
Dr. Hartman, can I ask a question?
Yes.
So is the controller the mechanism that is implementing the safety constraints to make sure the safety constraints will be facilitated?
I didn't understand.
So we said there is a hazard, right? And then if there is a hazard, there is a safety constraint, like maintaining the distance, right? So what is the role of the controller in this scheme? Is the controller facilitating the safety constraint because the controller makes sure that we will have the distance? Is that the conceptual?
Let's take the, because this is everybody's driving, I think, driving a car. So we are driving a car. The driver is a controller.
Okay.
He has a controller above him because someone gave him the driving license. Yes?
Yeah.
So he's not a unit for himself. So now he's driving. And he knows that there is a hazard, not keeping a safe distance, and therefore there is a safety constraint. You must keep a safe distance. I think the easiest way is to think, let's say we are building an autonomous car, and we have to think, because we know it, all this, how to do it, we know it. We are human beings. We have a brain like it's a fantastic brain. But once we try to teach a computer to drive like a human being, we find that it's very, very difficult. So we have to teach the computer of the autonomous vehicle that it has to keep the safe distance. It means that if, let's say, the other car slows down, he has to slow down. Or maybe he has to make a maneuver to go to the right or to the left and so on. So, and also we all the time change. I mean, driving, we play with the wheel because we don't drive exactly the same way all the time. So there is all the time, every millisecond, we actually are using this control loop to drive safe. Yes? Is it a good answer or?
I think it is. So what I understand is safety constraint is embedded in hazard. So when we have a hazard, we must have a safety constraint to negate it. And the controllers are the things that facilitate the safety constraints, that made the things that try to make sure the safety constraint is being implemented.
Yes, but again, we are talking now because before it, I was talking about socio-technical system.
Yeah.
But actually, the people who are sitting, the legislator, the people who are writing the laws in a country, yes, be it in the United States or be it in Israel or France or wherever, they have to know about the hazard. They have to know that they have to build this keep a safe distance everywhere in the system. Yes, not only in the mental model of the driver, but also in the green lights, in the signs, road signs, in the ability of the car to brake, to stop or to accelerate and so on. Yes, so it has to be everywhere, and therefore we are talking about system safety and not driver safety. Okay, so the controller needs to have a process model. He needs to know about the hazardous process, and he needs to have some algorithm to implement it. Yes? And again, it goes on and on. And Nancy Leveson, her students were sitting and thinking about where there can be flaws in this control loop, and they found different ways. Yes, I'm not going into it at the moment. But you can see it, and you have the material, and I go through it. Well, you have them. I will just skip because of time. Now, one of the questions is why this model and method demands so much work more than other methods. It's not true, but people think so. Why do we need it? So if we take a simple mechanical control structure, an electromechanical control structure, and a computerized control structure, we just can theorize. You see where the red X's are, the places where we have potential to make failures. And you can see that today's systems are complexer, need more or have more potential to have failures than the old mechanical or electromechanical systems. And therefore we need something more powerful, something more clever than the common methods in safety. So again, I will go quickly through my illustration. Yes, So we have, let's keep it. Okay. Now I'm using an illustration from a publication by a team of people from Greece. Yes, they used it for something else. And it's a very famous case study in our literature. It's about a train with a wagon, and it has a door, and the door can sometimes not be closed. And if it's not closed and the train is moving, people can fall out, and it's, of course, it's a loss event. So it's an accident. So let's take this case and say we have an accident, a person falls out from a moving train. And to this accident, you can actually reach, you can have this accident via 3 different hazards. And these 3 different hazards can have much more, about 20 unsafe control actions. And these unsafe control actions can actually be generated via 40 scenarios. Actually, it's just illustration, because people who are studying autonomous cars, for example, where we have a collision between 2 cars, they can have also 3, 4, 5. Normally, in a system, we don't have more than 5, 6 hazards, system hazards. And from 3 to 5 system hazards, we can have hundreds of unsafe control actions, and we can have thousands of scenarios. And actually, in the autonomous industry domain, there are people sitting and trying to find all possible scenarios that can lead to this accident of collision between 2 cars, because they have to teach the computer, the programs about it. And only STAMP and its tools can help us generate these scenarios and so on. So one of my advices to you who are looking have interest in STAMP, this is actually future, because with the help of STAMP and STPA, we can generate all these scenarios, understand all the unsafe control actions, and we can, of course, be more efficient than people are sitting with the old way of thinking and so on, and looking, trying to find all the scenarios. And just, again, we don't have time, but it's important, this slide, and I found that there is one mistake in it, but never mind. So here you have 3 different hazards. Following these hazards, you have 3 different safety constraints, and then following, they are not related, it's just a listing of 3, 3, and 3. And 3 unsafe control action. This control action actually does not belong to the 3rd hazard and 3rd safety constraint. But if we analyze many cases, people found out in Nancy Leveson group that actually these statements, yes, these unsafe control actions have a very fixed logical and verbal structure. Yes, there is always a source controller. Who is the controller in this unsafe control action? What type of unsafe control action? What is a control action? And in which context? Context is very important. For example, I was talking before about a person falling out from a moving train. But if the door is open and the train is aligned in a station, of course, it's not a problem, yes? On the contrary, if the door is closed and the people cannot go out, then it will be a problem or a hazard. So I already, 2.5 years ago, we had a project with students, with a computer student, or software students, and we used artificial intelligence, and we got very interesting results because we can put STPA analysis into an artificial intelligence system, and by teaching the artificial intelligence, after a while, it will do most of the work, because most of the work is just routine work, yes? Going again and again. As I said before, we can have thousands of scenarios, hundreds of unsafe control actions. It's a lot of work, and it makes you dull. And just a few weeks ago, another group, we didn't publish it, another group from UK just published. If you are interested, I can send you the publication. They use ChatGPT, and they show that ChatGPT can make STPA much easier than people were thinking before it. So as I said, I showed you before, very, very simplified system, or not system, but just loop. But of course, it can start getting nested and more complex with not one process, but with few processes. And we talk about system safety as emergent property. So all these control loops, yes, should be perfect if we want to have a safe system. Yes. Unfortunately, once we study accidents, disaster, and so on, we can see, and I will show you next lecture, that many control loops had problems, and therefore safety was not delivered. So 25 years ago, a Danish safety specialist, Rasmussen, if you are dealing with human factors, I'm sure you know his name. He suggested to use the concept of socio-technical system, starting from legislation, regulation, management, and then the flow, the hazardous process, as a construct for our system safety. And here you have a more detailed structure of it related to the state of Israel. You have a federal country, so you have 50 such, and then you have on top of it the federal structure. Your system is much more complex than our system. Nancy Leveson took the Rasmussen idea and said, no, we don't have one socio-technical system, but we have two. We have one socio-technical system which is responsible for developing a system. Let's say if we want to build an airplane, yes, there is a socio-technical system starting from legislation, how to build a safe airplane. And then we move the airplane to a company that operates it. And again, we have a system operation. So a legislation to operate an airplane is totally different from building it. Yes. Now we have some problems. Typical safety security focus will be in the operation on the floor, yes, down, and not what happened above. Is the legislation okay? Is the management okay? And so on and so forth. And also in the development, yes, the problem is that requirements and so on are not exactly checked and so on. So this is Nancy Leveson's system development and system operation. And I suggested to include a third system and this system response control structure. And I will give you two examples, and I think with it I will finish. 9/11, many people died, were killed during the operation of the buildings. No, it unfortunately happened. But many people were killed and died or suffered from the consequences also from the response. So the policemen, the firefighters, the other people who came to help and so on, they had no safety thinking before it. There were no plans, no design how to deal with such a problem. The same happened in Chernobyl. Chernobyl, most of the fatalities were during the efforts to respond to the catastrophe and not during the catastrophe. And therefore, in many cases, we need the third structure of safety response control structure. And again, I will just finish with not this. This will be for the next meeting. Okay, so we have this, and now you have 2 days to think about, do you prefer the common approach from risk through probability and impact to try to get safe system, or via the more complex model and more complex methods but I'm sure from my experience, it will lead to much better and safer systems. Yes, so think about it, and we'll discuss it next meeting. And next meeting also, I will bring you a few case studies. I hope you read about it a little bit, and we see how we analyze it. Again, only in a nutshell, not really into depth. Thank you, Nir, and
Thank you, Dr. Hartman. We really appreciate you.
Thank you.
Folks,
Yes.
have a good afternoon, and the next second part will be on Thursday at 2 p.m. Feel free to join us.
Sounds good. Thank you, everyone.
All right. Have a good evening.
Thank you, Dr.
Thank you.
bye.